Hi everyone. So today we are starting chapter 4. This is a pretty exciting chapter because we're going to start seeing what we're learning in this class apply to a lot of modern day technology. But, well, there's no but. So we're starting with the bipolar junction transistor because this is the one that can be much easier to explain from a physics perspective. So if you ever see some, computer advertisement or specifically like the computer processor, like, from AMD, Apple, or Intel, a lot of times they would advertise, our new processor has 10 billion transistor or something like that. And we're going to learn what this transistor is and how we use it. And that way we actually understand the fundamental makeup of all modern day computation today. This is where we're going to see how, the concept of transistor, even though the bipolar junction transistor that we're going to, describe physically is not exactly what they're building computers out of. They actually make it out of MOSFET. So it's a field effect transistor instead. But that's just a manufacturing convenience. It's not that they functionally are different. It's just not as easy of a shape to make a lot of bipolar junction transistor versus the field effect. Okay, let's just start talking about like a little bit of like history about this. So this technology is so important, of course. The Nobel Prize in 1956 was awarded to Shockley, Bourdin, and Breton, who were at Bell's lab, who made the first transistor. You can even see a picture here. I'm going to try to describe what we're seeing here. And we're going to see that the same parts are actually in what we're going to see in the bipolar junction transistor we're going to describe. So here you have a little bit of a darker material, and we're going to see that this is an N-type semiconductor. So this may start sounding familiar because you're just learning about diode. Similarly, this is DOM. Here's also another N-typed. Okay. In the middle here is the P-type transistor. P-type semiconductor. I'm not sure about this ordering. It could be the P's can be switched with N. I can actually probably look that up. But the main idea of a transistor is that you're basically sandwiching two types of semiconductor that makes up what I call the bread, and then you put a little sandwich meat in between them, and that has to be the opposite type of semiconductor, and this gives you a transistor. And once again, a transistor is nonlinear, meaning it doesn't obey Ohm's law, so you cannot, have some predictive current law, known as Ohm's law, that just gives you a constant that the voltage is proportional to the voltage. And it is also going to be our first power device, meaning it can actually amplify signal. So we're going to start seeing V out that are going to be bigger than Vin, where previously V out can only get as big as Vin and usually a little bit less, right? And we're going to start off with the simplest version of transistor. It gives you like a nice physics description of it, and that way we can understand how the basis of it work. And all other transistors work in a similar fashion physically, but their structure might be a little bit different just to make manufacturing a little bit easier to do. Okay. So basically, as I mentioned, a transistor is just three semiconductors sandwiched together. I always like this sandwich example. So we have a N-type in this case, two N-type, that's going to be the bread, and then you have a little sandwich meat, which is the opposite, in this case, the P-type transistor. And what I want you guys to do once again is watch this Sabine civil engineering video that I showed you guys on diode last time. It actually goes all the way to transistor in the last couple of minutes. So if you are in the class, you can just click on the link on Canvas. Those of you who are not in the current class, you can search for it by just searching for Sabine civil engineering, how transistor work, so where you see this video. It's a great animation, and it's very useful for students to learn how a transistor work and remember it visually, instead of just me trying to describe, little semiconductor sections to you. So I'll let you guys do that. Okay, welcome back. So I'm going to go through, I'm going to switch the order how the book covers it a little bit, because I think it skips to 4.2, which kind of describes how it functions, but I want to talk about the mechanism first. So this is actually in section 4.3 in the book. So as you saw in the video, the PNP transistor is just a p-type semiconductor sandwiched between two n-type. Okay, and so the n-type in this case are the bread, and these are normally doped and much thicker than the p-type transistor. And what's connected to it, let's scroll down here, are what's known as the collector and the emitter. And the name of these things will be very obvious because after we describe how they actually work. And these are connected to the n-type, the bread of the sandwich. The meat of the sandwich is the p-type semiconductor. You can see this in the red here. Okay, and it's thin and lightly doped compared to the n-type. So, and the connector that you're going to see from the outside as a device is called a base, and hopefully the name will also become obvious once I describe how these things, what the purpose of these connections are to these three parts of the semiconductor, three types of the transistor. Hopefully you guys can see where this, it's a diagram, right, compared to what Shockley, Bardeen, and Bertrand built, right? You can see that there's three things, and they're little metal-ish, right? And these are the semiconductor that squished together in 1956 to make the first transistor. Okay, so let's describe how this mechanism works. Okay, when you have a n-type and a p-type, just like when we did diodes, right? What happened is that a depletion zone gets created between the two. Okay, this depletion zone basically creates a little electric field. Wait, so the negative goes here, yeah. So the electric field points this way. Okay, it basically gives you kind of like a voltage drop across this diode. Okay, similarly, if you do this again with another, well, actually, since we're doing NPN, I want to add another layer over here, right? Similarly, you can on the other side of the p-type semiconductor, you can put an n-type, and that's what's been happening here, which is this transistor. Okay, so what happened is that the electric field, they all points towards the p-type semiconductor. So actually they both point inward. Okay, so since the electrons are the charge carrier in what we use as most metal, okay, if you're dealing with plasma, that's a little bit different, where both charge carrier both charges are charge carriers. So what happened is that the both electric field points inward. What happened is that then it basically becomes a diode where you always have one direction or the other being reverse bias. Okay, remember that when you have a diode, let me draw this, right? Oops. Right. Let's go over here, erase. Okay, we have, right, this IV curve, right? And then basically the diode will not conduct until you reach the diode voltage, VD, But then you have this reverse one where it's, you know, usually substantially very large before you reach the breakdown voltage, right? And this V diode is maybe like 0.65 volts. This V break may be like, 50 volts or something like that. So usually you don't run into that, and you shouldn't, unless it's a Zener diode, which will be designed for that. Sorry about that. I had to change the battery on my pen, so that's a lot better now. Okay, so let's describe how this, what happens when you sandwich these three different semiconductors together. So you get a depletion zone, right, between both sides of the PN junctions, okay? And so in the case that, so the current is blocked, right, between the base and the collector. I'm going to start using these words. The base to the collector, you cannot flow current this way, okay? You also cannot flow current the other way unless you overcome the diode voltage, right? Okay, so let's see what happens when whether or not you overcome this diode voltage or not. So we're going to set this diode voltage to be 0.65, okay? And we're going to denote that the voltage between the base and the emitter as VBE. Hopefully that makes sense. Okay, if the voltage VBE is less than 0.65 volts, the transistor is off. Okay, and that means all the transistor basically block any current from flowing. Okay, in this case, the current from the collector to the emitter, right, is almost zero. So we get this little leakage current. Okay, and even if, right, the voltage between the collector and the emitter is bigger than twice the diode drop, it still cannot push current through because one of the PN junctions is actually reverse bias. Okay, so the base, the turn on voltage for the transistor we'll be using is about 0.65, and let's say we have 12 volts on the collector, just to keep it a constant. Okay, usually that's denoted as VCC. And then the emitter, let's just tie that to ground. Okay. So a little caveat, right? The transistor is off, but there is still the possibility that the current can flow from the collector to the base. Okay, and that's because, right, this is a there's some leakage current that can occur, right, even though it's reverse bias. And let's say the base, right, your base voltage becomes greater than 12 volts. Let's say you put 13 volt here, then you actually can overcome this diode voltage, and you would run current actually from the base into the collector. Okay, and this is usually not what you want, and that's why typically when you have a base like this, you would connect a little resistor to it, just to limit the current that could flow in case some miswiring happened. Okay, so let's see what happens when the voltage between the base and the emitter goes above the diode voltage. Okay, 0.65 volts. That means the transistor turns on. Okay, I'm going to erase a bunch of this stuff so we don't start with a new drawing. Okay, so when the voltage across the base and the emitter can overcome this electric field, the diode voltage, right now I'm going to talk about this in terms of electrons. So I'm going to switch to green pen. Okay, right now, right, since you overcame this diode drop, the electrons are actually able to travel from the emitter N-type semiconductor into the depletion zone. Okay, in fact, it flows into the P-type transistor, P-type semiconductor. Okay, this creates a lot of free electrons in the region, and a tiny fraction of it actually flows into the base. Okay, these are electron currents. Okay, The reason it's tiny because we make the p-type transistor very thin, and we're also connecting it to the side of it. You can actually even see this up here on the original transistor. So the middle sandwich thing here, right? This is the little wire that's connected to it. So they made the p-type transistor large, but then they connect a tiny wire to it so that only a small amount of current flows that way. Okay. Oops, too far. Okay, so a small amount of current flows from electron current flows from the emitter to the base, but since in sign convention of electronics, of electricity and magnetism, we think about current as the positive charge. So what we think about is that there's a current that flows between the base to the emitter in the opposite direction. Okay, that's the deals with the sign convention. So what happened is that most of the electrons, go back to green, right, actually escape the depletion zone and goes through into the n-type collector semiconductor. And therefore, most of the current, actually, most of the electron current flows this way, and therefore, the sign convention current goes this way, and this is known as the ICE for the collector emitter current. Okay, so we get a little bit of base emitter current that are small, and then we get a much larger collector emitter current. Okay, in fact, this is known as the gain, the current gain of the transistor, and this is defined as the collector base current. Yes, let's do collector emitter current, right, is amplified by this factor of beta, where the beta is amplifying this base emitter current. Okay, and this value beta for the transistor we're using, it could be, for the ones we're using, it's about 100. There are some that are 200, 500, 1,000. The thing to know about is that this is not an exact number. So okay. I'm trying to move this out of the way down here. Okay. And it's not because that the semiconductor manufacturing is made it bad. It's because this is actually a temperature dependent value. So as you run the transistor, it may heat up a little bit, and it's very sensitive to that. So the beta value actually changes just as you turn on the transistor, no matter how well it's manufactured. Okay, and this is the transistor current control relation. That's what the book calls it. And that's the first equation in the textbook. Okay, I'm going to move this down. Yeah, I think it's got moved. Okay, so if the little video animation did not help, and my long-winded discussion did not help, there's also an analogy that really helped me remember this when I took this class 20 years ago from, well, now the famous John Martinez, that won the Nobel Prize just last year on quantum computers. So the way he taught it is that you can think about the transistor as kind of a little valve on a garden hose. So let's say you have some pipe, right? Let's always go to the water analogy. And on this pipe, you have a little valve that you can turn to turn on the water or not, right? Okay, so let's say the current is flowing this way, right? So this is actually the collector. There's actually this is not the emitter. The emitter is down here, right? And this is sort of like the base. So you can turn the valve a little bit, and then that controls how much current flows out of here. Okay, now maybe a better example is just to make it dead end, so you don't have another end of the valve. You just have a valve that's one end. Okay, let me let me redraw that, make it a little bit better. Okay, let's just say you have a end of a hose, at the end of a pipe, right? And that goes to a little valve that you have a little knob to turn, and depending on the position of this knob, right, it changes how much water comes out. Okay, and that's basically what you think about. And when you're dealing with transistors, the base voltage is kind of like that little knob that allows you to change the amount of current that you want flowing through your pipe. Okay. Since a transistor is basically two diodes sandwiched together, you can actually check the diode drop if you want. Well, you want to make sure that your transistor is working, because a lot of times they would burn and you may not even notice. So for a NPN transistor, right, the base is the p-dope material, the collector and the emitter are the n-dope material. Sorry, I think I said the opposite. The base is the p-dope, and then the collector and emitter are the n-dope. So what you do is you basically connect you want to connect the anode to the positive end of your DMM, and the cathode, which in this case will be the n-doped. So you basically just connect the red to the middle here all the time, and then you check, the collector and emitter, and whether or not you're getting this 0.65 volts. Okay, if you connected it backward, you just get a out of limit on your multimeter. If the transistor is actually broken on one side or the other, you also get this out of limit, or you get some weird other voltage, let's say. Okay, maybe like it'll give you like 0.1 volt or something like that. Okay, so the way we use this is by putting it into a circuit. So what we're going to do, we're going to have a symbol, a schematic symbol for it. For a NPN transistor, it's basically the way I draw it is you have, let's say you have a resistor coming in, you put a bar there first, and then you put two little legs, and depending if it's NPN or PNP, and where you want your emitter to be. Okay, for NPN, the little arrow always goes out, and so that basically defines this as the emitter. Okay, and let's say you have another resistor and it goes around here, and then you have some voltage source that you're using. Okay, and that's how you draw a transistor and a schematic. So how it works is that, right, the current flows from the collector to the emitter. Okay, and then a small amount of current flows from the base to the emitter, but of course this is almost negligible, because your beta is going to be something on the order of 100. Okay, so we would bias, right, the collector typically with a high positive voltage. Typically this is denoted as VCC. Okay, the emitter, sometimes you would tie this to ground just so you can have a low voltage, but sometimes you would tie it to negative VCC, right? Let's say your VCC is 12 volt, negative VCC will be negative 12 volts. Okay, and sometimes that's also called VEE, just so it's emitter, I guess. Okay, so, and the main thing I want you guys to know is that, okay, if the voltage between the base and the emitter is less than 0.65 volt, the transistor is off. Okay, and you will not get any current through the transistor. But once you go over that, okay, the amount of current that you get from the base to the collector is amplified by this beta factor. Okay, for the ones we're going to see in the lab, the 2N3904, this is an NPN transistor, and the diode drop is about 0.65 volt, and you get a beta value of about 100, and we can actually see this in the lab. Okay, as I mentioned before, this beta value is approximate, not because we cannot manufacture these things very well. It's just because this is a temperature dependent value. And Transistors on their own is actually extremely hard to control because this beta value just changes as you run it. So what we're going to do, we're going to start using, these things called operational amplifier and digital latches just to kind of remove these beta effect. Okay. Okay. So let's see what a transistor actually looked like in real life. So this is the packaging. So this is a NPN transistor. Physically, they look like little, to me, they look like little virus, actually. So they have a little head. One side is flat, the other side is curved. Okay. And the way you want to read this is that you want to look at it from the flat side for and the legs are always going to be collector, base, emitter. Sorry. You want to look at the flat side. Collector, base, emitter. It's always going to be that. Okay. So, did I talk about the PNP, the opposite doped transistor? Basically, what you do is you connect everything backward. And I'm going to make a little note. Actually, this is where the note is. Yeah. So NPN transistor and PNP transistor, they basically have the same functionality. So anything you can design out of NPN, you can make out of PNP. There are some application where having both is useful. In the lab, you're going to use NPN exclusively. I don't think there are any PNP laying around that's going to trap you. So in the PNP, I'm just going to describe it real quick because the book doesn't. Instead of connecting the VCC to the collector, this is usually what we connect to, right? You actually connect the VCC to the emitter instead. Oops, where did I put this? Okay, that's why they orient it that way. And in the case of a PNP, the arrow, right, actually goes into the transistor. So that's the main difference. So be a little careful, right? Because what I can do is I can draw this NPN transistor this way, right? You may think, oh, the arrow's on top, right? Therefore, it's a PNP. It's not. The arrow's going out of the transistor. That means it's a NPN. If the arrow's going into the transistor, it's a PNP, right? Because you can rotate these things up and down. Okay. So, and everything's kind of opposite with the PNP transistor. So instead of the base being higher than 0.65 volts, it has to be lower than negative 0.65 volts instead. Okay, so everything's just kind of, all the signs get flipped and the logic gets flipped. And you might think, like, why would anyone ever make this sort of stuff? Because it's just going to confuse you and make your circuit on fire because you connected a PNP transistor where you thought you were using an NPN. So one example I want to show you guys, this is not in the book, of course, is this push-pull amplifier. You're going to see this in a lot of other textbook. I found this drawing off the electronics tutorials website. They're not best at explaining how their circuits work, but I kind of want you guys to get the gist of how this works. So in this case, you have a little regular PNP transistor, and then beneath it you have a NPN transistor on top and PNP on the bottom. And what happened is that you have a signal that's an AC voltage. Okay, so when the voltage is positive, what happened is that it gets flow through this the top transistor. Okay, and then you're basically pulling current through the collector into ground here, and then you're actually able to drive your whatever device you're trying to drive the load. Okay, but when the AC signal goes negative, this transistor basically turns off, and that's why you connect a PNP transistor to it. So when the voltage is negative, okay, the collector actually draws current the opposite direction. So therefore, right, it still allows you to pull current through the load, drive the current through the load, okay? And that way you're not wasting half the negative end of your AC wave. Okay, it kind of works like that in the way that the full wave rectifier work. Okay, of course you could have built this out of 4 different NPN transistor, but right, you basically save 2 transistor by just having the PNP type. Okay, in the lab you're going to be using NPN transistor by default. I don't think we have any lab that actually asks you to use the PNP, which has a part number of 2N3906 instead of 04. So you should just assume that. But of course, if you plug it into your multimeter, you can actually test what it is. And usually it's very small. It's for me to read, at least at my age. But maybe you guys can see the part number on the transistor itself, actually. Okay, that's it.